The Zebra Zero robot system represents a significant advance in robot technology. It incorporates new control techniques which make it uniquely suited for the difficult task of automated assembly. Its advanced sensing and control features, coupled with a convenient user interface, enable a user to quickly develop complex assembly tasks with a minimum of custom tooling. The Zero's articulated configuration is similar to the popular Puma manipulators. It has base rotation and shoulder elevation joints, an elbow joint, and 3 intersecting wrist joints. The standard end effector is a parallelogram pneumatic gripper. The Zebra Zero is controlled by a modified IBM PC-compatible computer. The portable version of the controller is shown here. The Zero is programmed within a modern menu-driven environment. Programs can be modified and run immediately by the interpreter or compiled for standalone use. The entire control system runs under the standard MS-DOS operating system, affording a level of standardization and convenience not found in most industrial robots' homegrown controllers. What makes the Zero truly unique is its 6-axis force-torque sensor mounted between the wrist and gripper. As we push on the gripper, we can see displayed on the screen the forces and torques exerted on the gripper. This sensor is completely integrated into the robot control system. It not only detects critical force conditions, but it is also used in precisely controlling the contact forces between mating parts. This is a capability not available on any other commercial robot. Current industrial robots can only operate in position control mode. They can only move from one position to another, regardless of the forces they encounter. The simple task of inserting a shaft into a hole illustrates the extreme difficulty of performing assembly tasks with position control alone. In a typical assembly, the clearance between a shaft and hole may be less than 1/1000th of an inch. To position the shaft correctly, not only must the manipulator be this accurate, but the position of the fixture, the position of the part in the fixture, the position of the hole in the part, and the position of the shaft in the gripper must all be accurate enough so that the cumulative error is less than 1/1000th of an inch. If a CAD system is used to program the robot, the CAD model must also be this accurate. The engineering required to achieve this precision is expensive at best and sometimes altogether impossible. The ability to control forces offers a totally new approach to robotic assembly. Here, we show the Zero using force sensing and control to perform our sample task of inserting a shaft into a hole. First, we use the force sensor to detect when the shaft is aligned with the hole. The active force servos are then used to maintain contact while righting the shaft and to prevent jamming as the insertion is completed. As the task is repeated, we can see how the force control techniques are tolerant of significant misalignment between the shaft and hole. The Zero's ability to compensate for such sizable misalignments of parts can drastically reduce the cost of robotic assembly systems. Now, we will demonstrate force sensing and control techniques as applied to the assembly of a pop-up lawn sprinkler. First, the sprinkler housing is placed in the assembly fixture. Next, the pop-up stem is placed in the housing. If the arm encounters excessive forces, it stops and rotates the stem until the parts assemble smoothly. Note, in picking up the spring, the Zero's force sensor is used to detect if no part is present. In this case, the arm simply moves to the next spring in the pallet. Screwing on the cap is the most complex part of the assembly. The Zero first pushes down with a specified force to make sure the cap is seated properly. After rotating the cap, the Zero tries lifting it to determine whether the thread is properly engaged. If not, the Zero puts the cap back down, re-grasps it in a new orientation, and tries the threading process again. Completing the threading process requires that the arm move along the exact geometry of the thread. Rather than programming the exact thread geometry, as would be required with position control robots, the Zero uses a strategy of simply twisting the cap while pushing down with a specified force. By controlling forces rather than just positions, the Zero is able to complete the assembly without binding. As you have just seen, the Zebra Zero's force sensing and control technology, coupled with its standard control computer and modern programming environment, yields low-cost assembly systems developed with minimal time and effort.